The reason I picked these two examples to illustrate this calculation is this. If we look at the amount of the solid of each of these that dissolves, there's a different amount. So don't think that the KSP will tell us a particular amount of grams or a particular amount of moles that are going to dissolve in a particular solution. KSP is just a measure of how we can look at the equilibrium constant of a saturated solution. So when we're looking at these things, we can come up with the following statement. We can say that KSP and molar solubility are directly related when the cation to anion ratio is the same but since the ice tables are different with different ratios of cation to anion, some extra thought is required when comparing KSP and molar solubility. And I think this statement right here that I just said is best illustrated by performing an example. So the example problem that we can ask is which of the following slightly soluble salts has the largest molar solubility. And we're going to compare 5 of them. The 5 salts that we're going to look at are cadmium carbonate, cadmium hydroxide, cobalt hydroxide, silver iodide, and zinc carbonate. If we have these 5 salts, this question's impossible unless we have the KSP values. There's one of 2 ways that you'll get KSPs. One, they'll be mentioned right in the problem, or 2, we'll give you a KSP table attached to the end of your exam. So for the KSP values, for cadmium carbonate, the KSP is 5.2 times 10 to the minus 12. For cadmium hydroxide, the KSP is 2.5 times 10 to the minus 14. For cobalt hydroxide, it's 2.5 times 10 to the minus 15. For silver iodide, it's 8.3 times 10 to the minus 17. And for zinc carbonate, it's 1.4 times 10 to the minus 11. So here are our 5 values for the KSP. I will say one thing, and you're going to find this out when you write your lab report and put it together for the KSP of calcium iodate. In the discussion section, the instructions ask you to look up a literature value for the KSP of calcium iodate. This seems fairly straightforward, so we're going to go to our favorite reference source, which is Google. We're going to type in KSP calcium iodate, we're going to hit enter, and you're going to come up with millions of hits of all types of web pages that has a KSP value for calcium iodate. You're going to click on the first web page, you're going to find a value, you're going to write it down, and everybody's going to be happy, right? But some of you might be curious. You're like, okay, what if I click on the second web page? And you look at it, and there's a different value. And you're like, okay, well, which one's right? So that means we're going to go to the third web page on there and click on it, and yet it's another value. KSP values, look at these things. Look at the silver iodide up there, or silver iodide. 8.3 times 10 to the minus 17. That's a pretty small number. How easy do you think it is to measure that? It's tough. 8.3 times 10 to the minus 17, you know how small that freaking value is? So you're going to go through and you're going to see different sites. Depending on when the data was collected, the KSP values may fluctuate. Even if you look in one textbook to another textbook, the values will change. The reason I'm bringing this up is because you guys are using a computer program that grades the problems based on the KSP that it has inputted into the system. So I'm going to throw out a warning and a disclaimer that if you need a KSP value in an online problem and it's not there, don't Google something and look it up and use the first value that you find. Please email me right away and let me know that I need to post the KSP value for that problem. Okay? We ran into trouble with this last quarter in Chemistry 122, and to my knowledge, all of the quiz questions that are graded on the KSP assignment have the KSPs actually typed into the problem. I had to go through and manually insert a couple of those. So if you're doing a quiz problem and you see these KSP values, or you need a KSP value, please email me so I can post that up there. Okay? But KSPs are a little tricky, right? And they're tough to determine. And you're going to try to figure this out in that first experiment. So in your first lab experiment, rather than grade you based on how accurately you can calculate this value right here that might be argued in different scientific communities by experts, I want you to pick or find a website. Number one, you have to list your source because the sources are going to vary. Okay, make sure when you write your discussion that you have a little footnote with the reference that you use where you got your KSP. And what I want you to do is say, why is my KSP value different than what they state in the literature? What could have went wrong in our particular experiment to make it either too high or make it too low? And explain why. And I think that's a better learning experience than just saying, hey, minus 10 points for not getting the KSP out to 8 decimal places. Okay? So think about that when you're going through and you're writing your report together. Back to this example problem. Sorry for the little sidebar there. But we have a list of KSPs, and we want to know which one has the largest molar solubility. This is probably one of the favorite standardized test questions that you'll see, both from the American Chemical Society, from an MCAT, from a DAT, from a GR. I don't know if they have this on the GRE, but this is a question that they really, really like, because if you're not thinking, you'll pick the wrong answer. Okay? So step number one for this problem right here is we're going to group the salts based on cation to the anion ratio. So we're going to put these particular 5 salts into 2 groups. There's a group that I'm going to call AB and a group that I'm going to call AB2. The AB group is going to be the cadmium carbonate, silver iodide, and zinc carbonate. The AB2 group is cadmium hydroxide and cobalt hydroxide.